Hi, everybody, and welcome to Volcanoes That Created Ancient Oceans. Tonight, your imagination floats above a world that doesn't quite resemble Earth, not yet. Below you, the entire surface glows a dark red-orange, like lava bubbling on a stovetop. Jagged ridges rise and fall, endlessly reshaping as molten rock surges up from a furious, uncooled core. No blue skies here, just a thick orange haze, swirling with ash, sulfur, and the occasional flaming pebble. If you tried to walk across this early Earth, your shoes would last exactly 0 seconds. The planet is still forming, and frankly, it doesn't want you here. You'd melt, boil, or just disintegrate, whichever comes first. It's a bad time to visit, but a great time to start the story of oceans. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know where you're watching from and what time it is. Always fun to see how far this little bedtime voyage travels. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift lower through the haze, hovering over what could generously be called land. There's no clear ground yet, just solidifying bits of crust trying to compete with an endless sea of magma. Volcanoes don't erupt here. They are here. Everything is volcanic. The entire planet is a restless heat engine. Beneath the surface, a churning mess of molten iron, silicates, and radioactive decay keeps things lively and far too warm for anything resembling life. This is Earth, 4.6 billion years ago, young, angry, glowing. Back then, the moon had just recently slammed into Earth. Yes, the moon used to be part of us, but a glancing planetary collision sent a huge chunk of Earth sailing into orbit. It eventually became that gentle silver circle you see at night. Lovely now, but it was born from chaos. The collision left Earth tilted, scarred, and thoroughly traumatized. As a bonus, it kick-started an age of unstoppable volcanic fury. Mainstream geology agrees. In its first few 100 million years, Earth was completely covered in volcanoes. Not just those pretty cone-shaped ones we sketch in notebooks, but massive shield volcanoes that sprawled like entire mountain ranges. Some were underwater, some above, and many didn't care to pick a side. Their combined breathing filled the skies with steam, carbon dioxide, ammonia, methane, and sulfur dioxide, a cocktail that would make any atmosphere inspector quit on the spot. Fringe theories even suggest the entire crust was a mobile, semi-solid shell sliding around like a lava-filled blister. Earth's first continents, if you can call them that, may have just been slightly cooler blobs floating in a magma sea, jostling each other like soggy crackers in boiling soup. Historians still argue whether a solid crust existed at all in those early years, or if it was more of a crusty suggestion. But one thing is certain, the planet was anything but quiet. As you float through this volatile landscape, you might notice that some of these volcanoes seem to breathe rhythmically, swelling, groaning, then bursting with new rock. Each eruption belches more vapor into the thick sky. Some of that vapor? Good old H2O, water vapor. And there it is, the first shy appearance of the oceans. Not as drops, not yet, but as mist. Steam. Clouds thicker than soup and hotter than a sauna. Water, after all, was trapped deep in the planet's interior, bundled inside minerals forged during Earth's birth. And as those minerals melted and erupted onto the surface, they exhaled their watery breath skyward, over and over again for thousands of years. Now picture that cycle, looping endlessly. Magma rises, volcano erupts, steam escapes, skies thicken. But the Earth's surface is still far too hot. Any rain that dares to fall is instantly vaporized again. It's like trying to pour soup onto a stovetop, gone in a hiss before it hits. Still, the planet cools slowly. It has to. Radiation leaks into space. Night and day begin to form, even though the moon is much closer and the sun is far more energetic. Tides rip the early crust apart and churn the molten surface, helping release even more heat. Quirky detail time. Early models suggest that Earth's days were much shorter back then, somewhere between 6 to 10 hours long. Imagine that 6-hour days, hundreds of them a year, all spent under a sulfur-orange sky where it rains boiling acid. Great for productivity, though. You hover above the growing cracks in the crust. Where the surface cools just enough to harden, it fractures like a burned cookie. Beneath each crack, more magma waits, more gas, more steam. The cycle never ends. But one day, something shifts. One region slightly cooler than the rest allows a few precious drops of water to stay. They don't hiss into steam, they puddle, then they ripple, then they stay. The first permanent pools form. They're not oceans, not yet, but they're proof. The planet is ready to start collecting its tears. It will take millions of years, more millions, for the pools to connect, for the low points to deepen, for the trapped vapor in the sky to finally come home to rest. But this is the beginning. The fires are making room for water, and in this long exhale of volcanic heat, the stage is being set for something quieter, wetter, and full of possibility. The sky above you is thicker now, more gray than orange, more mist than flame. It's not cool yet, not by a long shot, but the magma oceans have stopped sloshing quite so violently. In their place, the land shifts, exhales, and glows like a campfire under damp ash. Earth is settling down slightly, and as it does, something invisible, yet deeply dramatic, unfolds above your head, the building of the Great Steam Blanket. Volcanoes, still spewing like there's no tomorrow, are now releasing not just steam, but a kaleidoscope of gases. Carbon dioxide drapes the atmosphere like a warm scarf. Methane bubbles up, lingers, and thickens the heat. Ammonia wafts in small plumes, sharp and eye-watering if you were actually breathing it. And all of this is happening before the first real raindrop decides to stay on the ground. It's strange, isn't it? For water to have filled the air long before it filled the oceans. But this is how early Earth worked. For millions of years, the skies were basically a giant steam room, cloudy, pressurized, and just waiting for a cool enough moment to let go. You float beneath this dense cloud layer now. There's no sunlight piercing through, just a gloomy amber glow from the churning ground below, and the occasional glint of molten rock pushing through a new fissure. The atmosphere by now is so thick it can trap heat like a thermal prison. This blanket keeps the surface warm, yes, but it also slows the cooling of the planet. Like throwing a wet towel over a campfire, the flames die slower, steam rises higher. Fun fact, if you had stood on this early Earth wearing a heat-proof suit and ignoring the lava lake at your feet, you'd barely be able to see a few meters ahead. The air would be a swirling fog of hot vapor and toxic gases. Not the best vacation, but one for the books. Historians still argue whether Earth's atmosphere at this stage was a help or a hindrance to ocean formation. Some claim it was too thick, holding in too much heat for water to condense. Others suggest it created just enough insulation to allow water vapor to pool, slowly, steadily into pockets of liquid over time. Meanwhile, the volcanoes don't quit. They roar like sleeping giants with allergies coughing sulfur into the sky in great plumes. Every eruption releases more water vapor, adding to the ever-thickening steam canopy. The planet is practically sweating, and there's nowhere for that moisture to go but up, and eventually down. Now picture this, a rainstorm lasting not hours, not days, but centuries. The earth, wrapped in clouds, begins to cry. Scalding drops fall from the sky, hissing on the rocks below. Thunder echoes across empty valleys. Lightning arcs between volcanoes like a silent conversation. And still, the heat is too intense. Most of the rain flashes back into steam the instant it lands. But the skies don't care. They keep weeping. Eventually somewhere, maybe a shadowed basin near the equator, maybe a crater shaded from the sun, some of that rain sticks. It lingers. It collects. The first warm puddles become ponds, and then maybe shallow lakes. And though they're still steaming like hot tea, they're real. Water has made landfall. Meanwhile, far above, the thick atmosphere begins to respond. Carbon dioxide starts dissolving into the forming water, reacting with minerals, drawing some of that gas out of the sky. The greenhouse blanket lifts just a little. And in that lift, the cooling begins to accelerate. The pace is still glacier slow ironic, since glaciers won't exist for hundreds of millions of years, but meaningful. Earth's climate starts to shift. The cloud cover begins to support more rainfall, more collection, more pooling. A feedback loop of wetness begins, all born from volcanic breath. Here's a fun tidbit you didn't ask for. Some researchers believe the color of the early sky was not blue, but a deep coppery gray thick with ash and moisture. The sun peeking through would appear distorted, redder than usual, barely visible behind the mist. Romantic if you're into apocalyptic landscapes. And all this time, volcanoes are doing the heavy lifting. Every explosion adds moisture. Every plume adjusts the sky's chemistry. Every lava field, once cooled, becomes a place where water might one day settle. They're not just destroyers, they're builders. Ocean architects in disguise. From a high vantage point, say, floating a few kilometers above the surface, you'd now begin to see sheen, wetness glinting where once was only rock. The first fragile hints of water gathering across the crust. It's not an ocean yet, more like a patchwork of steaming puddles, stretching across the uneven land. But it's a start, and all of it came from within the planet itself. Here's where things get delightfully speculative. Some researchers argue that this stage in Earth's history might have allowed for brief, almost ghostly appearances of clouds made of sulfuric acid. Yes, acid rain is an emperor in its purest form. Not exactly your gentle April shower, but chemically rich and important for shaping the minerals of the young crust. Others think ammonia clouds help trap just enough heat to keep everything from freezing too early. Volcanoes, it seems, aren't just spitting fire, they're writing the recipe for oceans, one ingredient at a time. Water vapor, heat, carbon, minerals, and the occasional dramatic lightning bolt for flare. As the centuries pass, you begin to see something beautiful. The lowlands begin to connect. One basin overflows into another. Rivers form not cool, clear streams, but thick, steaming flows of mineral-rich water, carving paths across young lava. They hiss and smoke, but they endure. Soon, the idea of an ocean becomes more than a dream. It's inevitable. The sky continues to give, the earth continues to cool, and the water, at long last, begins to stay. The first real ocean doesn't arrive with a roar. It arrives with a long, stubborn sigh. You drift now above a younger earth still angry, still volcanic, but softened at the edges. The land is no longer glowing everywhere. Instead, it simmers, a cracked mosaic of hardened crust and molten wounds. And in the low spots, something extraordinary is happening. Water is starting to stick. For millions of years, rain had been falling only to vanish again, boiled off the second it touched the earth. But now the surface is just cool enough, just shaded enough, just passive-aggressive enough to let the puddles stay. These aren't calm blue lakes. They're hot, metallic, and steaming like misbehaving tea kettles. But they're permanent, or at least trying to be. You watch one of these ancient puddles grow. It fills a basin formed by a collapsed volcanic caldera, a gaping hole where an eruption once blew the top off a mountain of magma. Ridges of obsidian line its rim. Mineral-rich runoff trickles down its sides. Each drop, scorching but persistent, helps fill the belly of what may one day be a sea. And it's not alone. All across the forming planet, these puddles that are multiplying, joining forces, a quiet uprising of water. But nothing about this process is peaceful. This is still a volcanic Earth, and it doesn't surrender territory easily. Every time a body of water begins to gather, there's a risk, a nearby eruption, a crustal collapse, or a sudden shift in plate boundaries could boil it away in minutes. Historians still argue whether these early ocean formations were stable or constantly recycled by the planet's volcanic tantrums. Some believe the oceans formed and evaporated multiple times before finally gaining enough ground to persist. Others argue they appeared once, but took eons to spread wide enough to be called oceans in the plural. Either way, what you see now is magical. The clouds are no longer fully suffocating. Patches of filtered sunlight pierce through the haze. The air smells like sulfur, salt, and ozone. Thunder murmurs gently in the distance. And beneath you, something is happening that has never happened before in Earth's entire history. A coastline is forming. It's a jagged one, sure, all cliffs and lava plains and weird stubby peninsulas. But it separates water from land, a true boundary, the first sign of a real shore. Of course, there's a twist. The water itself, it's a chemical stew, acidic, metallic, bubbling with dissolved yennies, more like a witch's cauldron than a tropical lagoon. And yet, it's water. Real H2O pooling from the sky and the earth alike, and it's here to stay. Let's slow down and talk about what that rainstorm looked like. Not lightning and thunder in the traditional sense, though there was lightning, for sure, but a near-constant drizzle that lasted millennia. Think about that. A global rainfall that spans generations of time, every drop pulled from volcanic vapor, every stream born from condensation. Fringe theorists like to imagine these first rains weren't even liquid all the way down. The atmosphere was so dense that droplets may have floated for miles before hitting the ground, suspended in steamy layers like sleepy jellyfish. Not so much falling water, but descending humidity with occasional ambition. Now your point of view widens. You rise above the landmass, past the steam layers, and look down through the thick atmosphere. And you see it, a blue-gray shimmer stretching across the curved edge of the planet. Still narrow, still shallow, but unmistakably an ocean. Not the Pacific, not yet. Not even the Tethys or Panthalassa. This ocean has no name. No fish, no coral, no songs echoing through the waves. It's empty, silent, and impossibly beautiful. Here's a fun geological detail. The minerals being pulled from the young crust into these newborn oceans are what start to give them character. Iron, magnesium, sulfur, even trace gold and nickel. These elements are dissolving into the water, giving it a strange, almost metallic behavior. It's not clear, it's not blue, it's rusty, a simmering broth of geochemical evolution. And yet, it's from this briny soup that life will eventually crawl out, blinking and confused. But don't worry, we're not there yet. First, these oceans have to last. Volcanoes, ever the drama queens, still threaten to take everything back. One particularly cranky eruption can heat the sky enough to evaporate entire regions. And there's always the chance that the early sun less stable than the one we know might throw a solar tantrum that pushes things too far. Scientists have even proposed that Earth came very close to losing its water forever in those early stages. One sharp tilt of balance, and poof ocean, gone. But Earth held on. One of the unsung heroes of this process? Clouds. Thick, stubborn, reflective clouds. As they formed from volcanic vapor and spread across the sky, they helped bounce some of the sun's heat back into space. They were Earth's natural parasol. Without them, the early oceans might have been cooked dry before they even finished forming. And so, between the bubbling lava, the thunderclouds, and the silent basins filling one drop at a time, Earth became a planet with oceans. You watch now as tectonic plates, still in their geological puberty, shuffle and twitch beneath the watery surface. Rifts open, underwater ridges form. Volcanoes erupt beneath the waves, sending up steam and ash and the occasional bubble of magma. The oceans aren't just passively lying there anymore. They're starting to shape things, eroding, cooling, pressuring, giving the planet a new texture, a new rhythm, a new quiet hum. And as you hover above this moment in deep time, you realize something humbling. This water, these oceans, they're still here, still in motion. The same molecules cycled again and again, from volcanoes to rain, to rivers, to tides. The same water that once hissed on lava now laps against your shower curtain. The same primordial drizzle that kissed volcanic cliffs now drips from pine needles in your backyard. And to think it all began with boiling rain that refused to go away. You descend again this time, through heavier clouds that cling low to the surface, damp and sullen. Beneath the mist, Earth looks almost peaceful. But don't be fooled. The ground is shifting, cracking, and bubbling from the inside out. Something colossal is happening beneath your feet. The crust, freshly formed and still fragile, is beginning to break apart. And those cracks? They're not just scars, they're invitations. Invitations for water to go deeper. Invitations for magma to rise. And together they're beginning to dig the first ocean basins. Welcome to the era of cracked crust and bubbling basins. The next chapter in the slow formation of Earth's watery heart. You glide above a newly formed rift zone, a place where the surface is tearing itself open, like slowly ripping warm bread. Gases hiss from the seams, magma pulses upward in a dull glowing rhythm, and water brave, boiling and relentless pours into these fresh wounds. Each time a slab of crust shifts, it exposes more of the molten mantle below. New depressions form. Some collapse inward, others rise, cooled by water trickling down through porous cracks. This dance of crust and magma creates something critical. Depth, because an ocean isn't really an ocean until it's deep. Shallow puddles can evaporate. Lakes can be erased by a good tantrum from the sun. But basins? Deep, rocky bowls forged by tectonic drama? Those can hold water, protect it, cradle it, let it build. This is how the first ocean basins were made, not carved gently by rain, but punched into the earth by shifting plates in the rising breath of volcanoes. It's plate tectonics meets angry soup pot. Mainstream geology calls these areas mid-ocean ridges today, but back then there were no oceans yet, just the idea of them. So what you see is more like a lacework of underwater mountains and valleys, stitched together by lava and ash. And then there's the bubbles. You float low now, just above a young, steaming basin. The water here is dense with minerals, hot, pressurized, and lively in all the wrong ways. Tiny bubbles rise from the seafloor, released from cracks in the rocks. Not air bubbles. Not yet. These are gases. Hydrogen sulfide, carbon dioxide, maybe a whiff of methane. They fizz and hiss and pop like a science experiment in a witch's cauldron. Some of these bubbling zones become volcanoes. Not the towering cones you'd see on land, but squat, oozing mounds known as seamounts. They erupt slowly, dribbling lava like melting wax. Each eruption adds new layers of rock, shaping the basin, deepening the floor, and occasionally even building islands. Brief, hot, and uninhabitable. Here's your quirky tidbit of the night. These underwater eruptions sometimes create bizarre structures called pillow lava. The lava cools so quickly when it hits the water that it forms blobs, like huge black marshmallows. They pile on top of each other, soft-looking but dense and solid, giving the ocean floor a strange blobby texture. You might say Earth was experimenting with beanbag geology, but even with all this crustal drama, Earth is far from finished. The continents, if we can even call them that, are drifting like half-baked cookies in a hot pan. Land masses are born and swallowed again, and each time one collapses or shifts, it leaves behind a scar. A deeper pocket in the crust, ready to be filled with seawater. Historians still argue whether plate tectonics was fully active at this point or just starting to assert itself. Some believe Earth's mantle was too hot for proper plate movement. Others suggest small-scale subduction zones already existed, chewing up bits of crust and fueling the ocean's birth. The truth may lie somewhere between, a chaotic trial period for the processes we now take for granted. What's certain is this: wherever the crust cracked, water followed, and wherever water pooled, volcanoes shaped the ground beneath it. This dance of fire and liquid, destruction and deepening, was the key to forming the first true ocean basins. And if you listen closely beneath the hiss and rumble, you might hear something gentle, the first hint of waves. Not the crashing kind, but long, low pulses of water moving across the forming ocean. Guided by wind, pulled by the moon, which, remember, was much closer back then, causing tides high enough to flood entire continents. Yes, Earth was moody, but it was also deeply creative. Now imagine watching the Pacific Ocean form not all at once, of course, but piece by piece. A trench here, a ridge there. Lava builds up, collapses, and builds again. Water rushes in to cool it, then stays. Thousands of generations of volcanic tantrums stack on top of each other until the basins stretch wider, deeper, broader. And eventually, they become the ocean. Today, we see ocean basins as stable, enduring features. But their origin story is volcanic, violent, and anything but peaceful. They are the world's deepest scars filled with water, yes, but born from fire. And it's not over. Even now, new crust is being made beneath the seas. The Earth's plates are still on the move. And deep below the Atlantic or Pacific, new cracks are forming, new magma is rising. and the ocean continues to shape itself. So the next time you stand at a beach watching waves roll in, remember, you're looking at a living thing, a breathing, shifting memory of a planet that cracked open and filled its wounds with water. And somehow that wound became home. You drift now far below the surface of those ancient oceans, down past the warming layers, past the shifting light, into a world so black it swallows thought. Down here, sunlight never arrived, not even once, but something else does. Heat, strange, invisible, bubbling heat. You're floating in the crushing silence above one of Earth's first deep-sea volcanoes. It doesn't roar, it simmers. From the cracks in the ocean floor, it exhales mineral-laced water hotter than boiling point, though. Thanks to the pressure, it doesn't boil. Instead, it vents. And just like that, you've arrived in one of the most alien, most important places in Earth's history, the realm of pillow lava and black smokes. These are hydrothermal vents, a concept that wouldn't even be discovered until the late 1970s by human submarines snooping around the Galapagos Rift. But here they are now, over 3.8 billion years ago, busy shaping the very chemistry of the ocean and maybe even the origins of life. A hydrothermal vent looks like a chimney built by a dragon with a flair for sculptural drama. Columns of mineral deposits build up over time as scalding hot water rich in hydrogen sulfide, iron, manganese, and other goodies blast out from cracks in the seafloor. When that water hits the cold ocean, the minerals precipitate instantly, forming dark, smoky plumes that drift upward like underwater ghosts. It's beautiful, in a terrifying way. Your eyes adjust to the darkness, and now you can see it better. A network of glowing cracks, each puffing and steaming like a line of overworked kettles. Between the plumes, strange rocks shimmer. Some gleam with metallic luster pyrite, perhaps. Fool's gold, born of real heat. Here's a fun, fringy tidbit. Some researchers believe that life didn't just survive near these vents, but originated there. The idea is that the unique chemistry, temperature gradients, and isolation of these underwater smokers provided the perfect lab bench for early molecules to assemble, flirt, and eventually boot up the first living cells. Mainstream theories still debate it. Some prefer a tide pool model life, beginning in shallow coastal puddles, bathe in sunlight, and occasional lightning. Others lean ventward, pointing out that here, in the pitch black, you don't need sunlight. You just need heat, water, and the right chemistry. Historians still argue whether hydrothermal vent communities were the first ecosystems or just among the oldest still active. Either way, these chimney fields are time capsules, ancient ones. Now, about that pillow lava. You look over to the left, and there it is, a slow eruption. Lava seeps out of a crack like syrup on a cold plate, cooling instantly as it meets seawater. It balloons, then bursts, then again, and again. Soon you have dozens, then hundreds of these soft-edged, bulbous rock forms piling up like a giant stone beanbag collection. Pillow lava doesn't explode like on land it oozes. Its smooth, rounded shapes help geologists today recognize ancient underwater eruptions in places that are now dry land. Yes, your local hill might have once been a lava pillow under a primordial ocean. And the ocean water isn't just watching, it's changing. The minerals being puffed out by these vents are dissolving into the surrounding sea. Iron-rich water turns the ocean murky. Sulfides mingle with hydrogen and carbon, creating bizarre chemical gradients. Over time, these reactions begin to support life, not photosynthesis, but chemosynthesis. Organisms that don't eat sunlight, they eat heat. You move closer to one of the vents, and now you see them. Weird, tube-like creatures swaying in the current. Giant clams with no mouths. Filamentous bacteria forming mats like wet silk. All of them living in pitch darkness, feeding on the Earth's breath. In modern times, these are called extremophiles life forms that thrive where no sane biologist would look. But in ancient times, they may have been the only life. The first communities. The first neighborhoods, all nestled around underwater volcanism, and they thrived. Quirky fact incoming, there are bacteria living near today's hydrothermal vents that can withstand temperatures over 120 degrees Celsius. That's hotter than the boiling point of water. They're not just surviving, they're comfortable there, like bathrobes in a volcano, comfortable. It's humbling to think that while land was still an unlivable nightmare of lava, ash, and acid rain, the ocean floor was already alive, quietly, invisibly, steadily. A kingdom of microbes doing their strange little dances, completely unaware that one day their descendants would invent pizza. Above the vents, clouds of black smoke drift gently upward, only to fall again in a lazy snowfall of minerals. These particles eventually blanket the ocean floor, forming dark, nutrient-rich sediments. Over millions of years, they become part of the rock record tiny fossils of geochemical poetry. You reach your hand out, figuratively, and run your fingers through the warm, mineral-rich water. It's soft here, heavy, alive in ways that don't yet involve anything with a brain. But it's beginning. The stage is being set. Because once you have water, heat, minerals, and a quiet place to hide from cosmic rays and asteroid tantrums, you have the perfect cradle. The Earth, despite itself, is becoming a nursery. And volcanoes, those explosive, dramatic diva monsters of geology, they're the nannies. Loud, unpredictable, messy, but ultimately essential. Without their breath, their heat, their endless supply of weird chemicals, this whole grand experiment might never have left the bubbling stage. So as you float above the quiet smokers, the wiggling tube worms, and the rolling pillows of lava, just remember, the ocean was never silent. It always had a heartbeat. It just didn't sound like ours. You're still deep underwater, far from the sun, where the silence feels thick and timeless. But now the water's changing. It's not just hot and smoky anymore. It's becoming salty and metallic and weirdly reactive. Welcome to a strange moment in Earth's early transformation, when the oceans first began to gather their flavors. This is the age of soy sedim and serpentinization. Let's start with the salt. At first, the water was nearly pure, a product of vapor condensing and falling from the sky. But as it rushed across the scorched crust, every molecule started picking up hitchhikers. Sodium, calcium, magnesium, chloride. They dissolved into the oceans, particle by particle, drop by drop. Today, we call these dissolved ions salts. Not just the table salt on your fries, but dozens of elements all swirling in solution, giving seawater its signature taste and density. That saltiness? It was born right here in the volcanic heart of a cooling world. You hover over an area where seawater has seeped down through cracks in the ocean crust, soaking deep into the rock. The water heats up, reacts with the minerals, and then rises back to the seafloor, vents changed. And that, dear dream floater, is serpentinization. It sounds like a magic spell. Honestly, it kind of is. Here's what's happening. Seawater meets a type of volcanic rock called peridotite, which lives just below the oceanic crust. When water flows through this rock, it triggers a chemical reaction. The rock absorbs water and transforms into a flaky, greenish mineral called serpentine. It literally changes form, hence the name. But it doesn't stop there. These reactions release hydrogen gas, tons of it, a precious, flammable ingredient for the beginnings of life. Hydrogen, when mixed with carbon dioxide and other gases, becomes the starter dough for organic molecules, sugars, amino acids. Maybe someday RNA. Serpentinization doesn't just change rocks, it changes possibilities. Here's your quirky side note. The name serpentine comes from its smooth, scaly, look-like snake skin. Some of the oldest serpentinite formations on Earth are over 3.8 billion years old, which means these processes have been happening almost as long as the oceans have existed. The planet was baking its mineral cake from the inside out. Historians still argue whether serpentinization zones were the true chemical engines behind life's origin. Some see them as quiet side characters, important, but not center stage. Others argue they were the first factories for biochemistry, providing warm, alkaline, hydrogen-rich environments ideal for early molecular tinkering. Now back to salt. As you drift over a newly submerged volcanic plateau, the water sparkles with tiny mineral particles, just barely visible if you squint through the haze. These particles are the ocean's seasoning. As they dissolve, the water becomes denser, heavier, and slightly more structured. This is the beginning of ocean chemistry. It's not just hot water anymore. It's a reactive soup, part volcanic exhale, part crustal erosion, part atmospheric gift basket, and it's always changing. Rainfall carrying dissolved gases adds to the mix. Volcanoes beneath the sea add even more iron, manganese, silica, rare metals. The crust gives and the ocean takes, and each chemical exchange nudges the Earth closer to balance, or chaos. By now, the oceans have a definite taste. If you could sip them, not recommended, you'd notice they're acidic, rusty, and slightly briny. Nothing you'd want to bottle and sell, but over time, as atmospheric CO2 decreases and reactions stabilize, the oceans begin to resemble what we know today. And yet, beneath it all, serpentinization still hums. You drift toward a crack in the ocean floor, where seawater is diving downward, drawn by gravity, pressure, and chemical hunger. It slips into the rock, triggers reactions, and reemerges through a vent some kilometers away, transformed. You watch hydrogen bubbles rise like pearls, trailing warmth and strange smells. If you listen closely, the seafloor is whispering. It's worth noting that serpentinization zones today still exist and are being studied by submarines, drones, and sleepy-eyed graduate students. Places like the Lost City hydrothermal field in the Atlantic offer a living glimpse into the chemistry of early Earth. There, entire spires of carbonate rock stretch from the seafloor like ancient cathedrals. They're white, not black like the smokers. Alkaline, not acidic. Gentle, not scalding. And yet, they're just as magical. Imagine one of these vents, billions of years ago, quietly puffing warm, hydrogen-rich fluids into the sea. No explosions, no flashy eruptions, just chemistry and peace. The kind of peace that could coax molecules into life. Here's something dreamy. Scientists have recreated serpentinization in the lab, in tiny sealed chambers. They've watched amino acids, yes, building blocks of life form spontaneously under those conditions. No lightning, no UV, just heat, pressure, and minerals. It's like Earth was trying recipes before anyone showed up to taste them. Of course, not every experiment worked. Some basins overflowed with incompatible elements. Some vent systems collapsed under pressure. Sometimes the chemistry veered into oops territory, uninhabitable pockets, acidic swamps, explosive interactions. But Earth kept trying. And as the ocean grew saltier, denser, and more complex, it also grew more welcoming to structure, to reaction, to patterns, and eventually to life. So tonight, as you picture these quiet cracks in the ocean floor, imagine them as ancient laboratories, hidden, steaming, whispering to molecules, over and over again. And while the surface of Earth remained a dangerous circus of fire and ash down here, the ocean was practicing patience. The minerals arranged themselves. The salts settled in. The serpentine stones curled like sleeping reptiles. And the water listened. Now follow the warmth. Warmth. Not the scalding lava of the surface, but the gentle, steady warmth from below, the kind that seeps, not explodes. You're gliding now above the ocean floor, somewhere between the volcanic ridges and the cooler plains, where warmth rises in waves, not blasts. And in this hidden realm, something delicate is beginning to happen. This is the birth of convection currents, a slow, looping dance of hot and cold that would come to sculpt the ocean itself. Let's zoom in. Picture a wide stretch of seafloor. Beneath it, the mantle is still restless, molten in parts, solid in others, always on the edge of motion. The heat from deep below rises upward, warming the rock above it. That rock expands slightly, becomes less dense, and starts to lift just barely. Above it, the crust bulges, forming long underwater ridges. These are the beginnings of the mid-ocean ridges you might recognize on today's maps. Then the water above responds. Like soup in a pot, the ocean starts to move. Slowly, invisibly, but it moves. Hot water from below rises through tiny fractures and hydrothermal vents. It spreads along the ocean floor, loses its heat, and sinks again. Then the whole thing starts over. This right here is Earth's first long exhale, a planetary breath cycle, stretched over thousands of years. Hot rises, cool falls, heat spreads, chemistry churns. And that movement, it matters. It matters a lot because oceans don't just sit there. They move, they swirl, and in those swirls, they mix their ingredients. Minerals from vents are carried to faraway places. Gases from the atmosphere are pulled down into the depths. Tiny particles begin to suspend and settle. Without this circulation, the ocean would have stayed static, a boiling, salty puddle with no rhythm. But with it, it starts becoming a system. Mainstream scientists agree that ocean currents, even in this early form, help distribute heat and chemicals across the planet. They prevented extreme local conditions. They stirred the soup, quite literally, and they laid the groundwork for the next phase, complexity. But even now, it's not just about heat. It's also about cracks. You drift along one of these long underwater ridges. The ground beneath you is breathing, cracking open along fault lines, releasing pulses of warmth and new lava. This isn't violent volcanism anymore. It's steady, constructive, like the planet finally figured out how to knit instead of punch. From these fissures, new crust is born. Thin sheets of basalt slide outward like slow tectonic pancakes. As they move, they drag the ocean floor with them. This is sea floor spreading, a process that continues to this day, adding a few centimeters of new crust every year to places like the Atlantic Ocean. Fringe geologists love this part. Some believe the earliest tectonic systems were chaotic, with tiny microplates drifting like puzzle pieces too small to connect. Others suggest that even in its youth, Earth had a functioning conveyor belt system, primitive, sure, but recognizable. Historians still debate whether these early convection loops were strong enough to shape continents. Some think they were limited to small ocean basins. Others suggest they influenced global patterns of heat and chemistry long before continents were more than squishy suggestions. What's certain is this: convection brought consistency. And with consistency comes predictability. Picture a tiny bubble of hydrogen sulfide gas, born in a vent deep below. Thanks to a passing current, it drifts sideways instead of upward. It carries its chemistry into a cooler, less hostile zone. There, it meets a carbon-rich molecule. They swirl, merge, and by some impossible alchemy stick together. That's how complexity begins. Not in violent flashes, but in gentle meetings, carried by water that moves. You float up now, away from the ridges, and see the greater picture. The ocean, once still and chaotic, now shows signs of rhythm. Not like the tides of today, but ancient primitive pulses. Warm flows hugging the seafloor, cool water descending from the surface, tiny vortices spiraling through the mineral soup. And in this movement, something poetic happens. Distribution. Iron from the western ridge now reaches the eastern basin. Phosphates stirred near the equator drift toward the poles. Thermal gradients push and pull everything, creating contrast, opportunity, difference. And with difference comes potential. Imagine early organic compounds, simple, unstable things, forming in the warmth of a vent, then carried into cooler waters. There they stabilize. Then they drift again, maybe to an area rich in clays or silicates, where they adhere, accumulate, and evolve. Without this movement, they just dissolve. But now the ocean is carrying messages. Here's a cozy science fact. Some of today's oldest rocks are found in places like Greenland and Australia, contain subtle isotopic signatures that hint at early ocean currents. Ratios of oxygen and carbon suggest water wasn't just present. It was moving, slowly sculpting both rock and chemistry. And over millions of years, these gentle loops of heat and salt shaped not just the ocean, but the atmosphere. As seawater absorbed gases from the sky, CO2 especially, it began to shift the balance. Earth cooled slightly. Rainfall patterns changed. And the feedback loop of ocean and air grew tighter. Your last glimpse for now, a wide basin, still young, still surrounded by volcanic scars. Steam rises from scattered vents. Mineral clouds drift like underwater weather. And somewhere, in a quiet eddy between warmth and salt, two molecules swirl around each other. They don't know it yet, but they're going to become important. Now imagine the ocean's breathing, not just in and out like lungs, but breathing with time itself. Long, slow, planetary inhales. warm currents creeping across the seafloor, then deep glacial exhales, cold water sinking, pulling life and chemicals into the abyss. Tonight, you're floating above one of Earth's first global circulations, not just random loops, but a coordinated planetary pattern that ties the oceans together. And this, more than anything else so far, begins to shape what the world can become. The ocean is no longer a disconnected set of basins and puddles. It's a network. The crust, cracked and restless, now pulses heat in regular waves from spreading ridges and vent zones. In return, the water circulates. It listens. It flows. Let's talk about one critical ingredient now swirling into this system: carbon dioxide. At this point, Earth's atmosphere is heavy with volcanic CO2 belched out constantly from eruptions, vents, and gas seeps. But the oceans, they're thirsty. CO2 dissolves readily in water, especially cold water, and the ocean is acting like a sponge. You hover now over the edge of a deepening continental shelf. Here, the water is cooler, pulled by slow convection down into the dark. As it sinks, it carries absorbed CO2 with it, stripping it from the air. This quiet chemistry is helping cool the planet. Yes, volcanic activity is still high. Yes, the greenhouse effect is still humming. But now the oceans are playing tug of war. They take in heat and carbon, cycle it, and lock some of it deep below in the cold, pressurized dark. Historians still argue whether this natural carbon pump was enough to stabilize early climate or whether Earth's temperature swings were still wild and chaotic. Some data suggests Earth nearly froze solid around this time. Others argue it was more of a lukewarm wobble enough to shift ecosystems but not destroy them. Still, what matters is balance, and the oceans were beginning to provide it. You drift further now to a boundary zone, a place where warm surface water meets the cold depths. Today we'd call it the thermocline, but back then it was just a ghost of difference. A line drawn by heat, by movement, by tension. Here, early currents press against each other. Warm water, rich in surface elements, slides above the denser cold. That cold water is nutrient-rich, pulled from the deep, where minerals and gases accumulate. When the two mix gently, slowly, it's like an underwater handshake. Something extraordinary starts to happen. Upwelling. Cold, mineral-heavy water begins to rise at specific places, drawn up by winds and currents at the surface. It brings phosphorus, nitrogen, iron. And where these nutrients rise, even in the absence of oxygen or light, the conditions for life sharpen. It's no longer just a chemical soup. It's a layered soup, structured, shifting, and strangely supportive. And now we meet the newest guests at the party, stromatolites. Wait, what are those? Imagine a slimy mat of microbes clinging to a shallow coastal rock. They're simple cyanobacteria mostly, and they spend their days capturing sunlight, absorbing CO2, and releasing oxygen as a byproduct. They layer over themselves again and again, forming weird, bumpy mounds that look like stone mushrooms or coral pancakes. And here's the kicker. These aren't just any microbes. They're photosynthesizers, the first to hack the sun. You might be thinking, hold on, we were just talking about vents and darkness. And you're right, but now with ocean circulation improving, surface layers are becoming more stable. There are calm shallows. There's sunlight, and where light touches water, life blooms. You float now above a warm tidal shelf. The water is still, kissed by the sun. And down below, those stromatolites are pulsing softly. Not dancing, not blinking, just growing, patiently. Cyanobacteria are the unsung engineers of Earth. By breathing out oxygen, they start changing the air above. At first, it's barely detectable, but over time, it builds, and that will change everything. Here's your fringe tidbit. In certain places, fossilized stromatolites dating back 3.5 billion years have been found still layered on top of one another, like ancient microbial lasagna. Some scientists think their spacing and shape indicate early forms of competition, even cooperation between microbial colonies. And yet they had no brains, no nervous systems, just chemistry, sunlight, and instinct. Imagine them as tiny solar panels, working tirelessly day after day, totally unaware they're creating breathable air for future mammals who'd invent decaf coffee and phone chargers that don't work. But we're not there yet. Instead, focus on the interaction between ocean and atmosphere, between vent and tide, between warm and cold. Each swirl of water is a potential experiment, each circulation loop a chance for compounds to meet, merge, and mutate. The oceans are now so much more than containers. They're labs, moving, bubbling, collaborative. Scientists today still trace nutrient loops through the ocean using isotope ratios. Some patterns we see now, like deep Antarctic circulation or Pacific gyres, might have ancestors in this ancient world. Slower, simpler, but conceptually similar. Back then, these patterns weren't driving fish migrations or coral reef rhythms. They were carrying molecules, spreading chemistry, providing consistency to chaos. And through it all, volcanoes kept bubbling, vents kept hissing, but now their voices were joined by another, the soft shimmer of photosynthesis, the quiet rise of oxygen, the gentle rise and fall of tides that would, billions of years later, guide crabs to shore and lull humans to sleep. Tonight, the oceans feel calm, but they are doing something monumental. They are making space. Space for life, space for balance, space for evolution, one wave at a time. Let's head back to the shore now, but keep your slippers on. You're hovering over an early coastline, if you can even call it that. There are no palm trees, no soft sand, just jagged volcanic rock, sharp cliffs, and tide pools that hiss and steam with leftover heat from the Earth's molten youth. And in these in-between places between land and sea, some of the strangest, most important things begin to happen. Welcome to the age of tidal pools and molecular mischief. Imagine the scene. The tides are still extreme, thanks to the moon being much closer, big, bold, and tugging hard at the newborn seas. Water surges inland, flooding cracks in the crust, then drains back hours later. Over and over, it's like the planet is learning how to breathe with rhythm. These early tide pools are strange creatures of their own. One moment, they're bubbling with seawater warm, salty, and full of dissolved minerals. The next, they're left high and dry under the infant sun, concentrating whatever was inside. Here's where things get tricky. As water evaporates from these pools, whatever it was carrying amino acids, sugars, tiny lipid blobs, gets left behind. It concentrates, it dries, it cooks. Then the tide returns and everything rehydrates, stirs, and tries again. This wet-dry cycle becomes a chemical slot machine. Spin after spin, molecules combine, break apart, and recombine in new ways. Over and over, quietly, endlessly. Mainstream science calls this the tide pool hypothesis for the origin of life. It argues that Earth's coastlines, with their rhythmic cycles and rich chemistry, were perfect playgrounds for prebiotic molecules, especially before enzymes and membranes evolved to keep things organized. Fringe thinkers go even further. Some suggest these pools were like primitive brains, not in the literal sense, but as systems capable of memory, repetition, and self-modification. Molecules here learned how to stick, fold, store energy, even protect themselves inside lipid bubbles protocells, the great-grandparents of all things squishy and alive. Historians still argue whether tide pools beat hydrothermal vents in the race for first life. Some say the sunlight and air exposure of the surface gave pools the edge. Others stick with the deep, stable chemistry of the seafloor. The debate is alive, much like the soup it describes, but no matter who wins, tide pools brought something new to the table: variation. Each pool had different chemistry, different sunlight angles, different rock types. Some had iron-rich basalts. Others were laced with clays, which helped molecules stick and align. Some were acidic, some alkaline, and every one of them, every single one, was a chance for chemistry to try again. Now let's peek into one. You see a glossy film on the surface, a rainbow sheen of oily lipids trying to form something like a cell membrane. Inside, a tangled mess of molecules. Some are falling apart. Others are forming chain-short peptides maybe. One lucky molecule just managed to replicate, using a neighbor as a template. Replication, that's a big one. Suddenly, we're not just talking soup, we're talking evolution. Because once a molecule can copy itself even badly, it can change, compete, improve. And if some variations help it survive better in these tricky tide pool conditions, well, that's natural selection, baby. Microbe style. Don't picture these pools as clean or calm. They are chaotic, bubbly, funky. Their chemistry shifts with each wave, each raindrop, each gust of wind, but that's exactly what makes them powerful. They keep changing. And change is fuel. Here's your quirky tidbit for tonight. Some experimental biochemists in modern labs have successfully recreated tide pool-like conditions, cycling heat, water, salts, and watch simple molecules spontaneously form membranes, join into polymers, and even replicate. In glass dishes, using no living enzymes, just heat, water, and time, and a bit of nerdy hope. Now look up, yes, up from the pool's glossy surface. The sky is thick with volcanic haze, but light still gets through. Not warm and gentle like today's golden hour. More like an alien sunset. Harsh, reddish-orange, filtered through a CO2-rich atmosphere and possibly streaked with methane clouds. But still, light. And some of those molecules in the pool? They're absorbing it, reacting to it, using it to jumpstart chemistry. These are photoreactive compounds, precursors to pigments, perhaps. One day their descendants will become chlorophyll and retinol, but for now they're just soaking it in. Everything is potential. You drift along the shore now, passing dozens of tide pools, each whispering its own version of the origin story. Some are drying out completely, leaving crusts of salt and clay. Others are newly filled, frothy with organic bubbles. All of them are playing, experimenting, failing, trying again. The ocean itself watches quietly, its larger, deeper self still stewing in its own hydrothermal dramas. But up here, there's creativity, risk, sunburn. And somewhere perhaps is already, or perhaps tomorrow, a molecule will copy itself well enough to survive another cycle, then another, then another. And life, fragile and unknowing, will begin. All because the moon pulled the tides, because volcanoes shaped the coastline, because seawater splashed where it wasn't supposed to go and molecules got stuck in a puddle. We don't remember these pools. No fossils remain of them. No shorelines from that time survive. But the echo of their chemical laughter is inside every cell you've ever had. So next time you visit the beach and the tide pulls back to reveal a shimmering puddle in the rocks, imagine, Restal, you might be looking at a mirror, a memory, of the first breath, of the first bubble, of the first brave, clumsy step toward everything. You're standing on that same jagged coastline, staring out at the ocean that birthed the beginnings of life. But now look beyond the tide pools, beyond the bubbling hydrothermal vents, beyond even the drifting protocells in their chemical waltz. Tonight, you're floating into the age of strange skies and oxygen dreams. Above you, the atmosphere is thick alien, rust-colored, and utterly unfriendly. There's barely any oxygen. Instead, the air is heavy with carbon dioxide, nitrogen, and traces of methane and ammonia. It's a cocktail fit for chemistry but not for lungs. Yours, anyway. This is the sky-earth war before it knew blue. Yet deep in the oceans and scattered across sunlit tide pools, something has begun to stir. Photosynthesis. Remember those stromatolites? The lumpy, bubbly colonies of cyanobacteria that spend their time sunbathing and bubbling oxygen? They're multiplying, quietly, patiently, persistently. And the more they breathe out oxygen, the more that oxygen lingers. Not for long at first. The planet's rocks and oceans are hungry for it. Oxygen reacts instantly with iron in the water, turning the oceans red literally. You look down and see it, bands of red and black on the seafloor, forming banded iron formations. These layered iron-rich rocks are Earth's receipts evidence that cyanobacteria were photosynthesizing long before the air could hold a single lungful of O2. Mainstream science agrees that these formations mark a massive transition in Earth's history. They record the slow buildup of free oxygen as it reacted with dissolved iron in the ocean, forming solid rust that settled in layers, like rings in a planetary tree. Historians still argue whether the oxygenation was a smooth curve or a sudden spike. Some say it took hundreds of millions of years of slow accumulation. Others point to a dramatic event, the Great Oxidation Event, around 2.4 billion years ago, where oxygen levels suddenly shot up and began to reshape the world. But here's where things get poetic. The early ocean was rusting itself into clarity. You're drifting now over an ocean tinted not blue, but a dull, coppery red. Oxygen bubbles drift upward from microbial mats in the shallows, only to be captured by the iron-hungry water. The planet is detoxing itself, slowly, blindly, with no plan, but with perfect persistence. Meanwhile, in the skies above, something else begins to shift. UV radiation still bombards the surface. There's no ozone layer yet to absorb it, but as oxygen continues to escape the oceans and enter the atmosphere, something extraordinary begins. The formation of ozone. Ozone, O3, is just three oxygen atoms linked together. It forms when O2 is zapped by ultraviolet light, splitting and recombining. And once ozone starts accumulating high in the atmosphere, it begins to shield the Earth from UV. You can't see it happening, but you can feel it. A softening of the light, a gentler glow at the edges of the day, a whisper that maybe, just maybe, the surface could become hospitable. Here's your quirky side fact. Oxygen wasn't always welcome. To many early anaerobic microbes, it was toxic, poison, a corrosive invader. And when oxygen levels began to rise, a mass extinction followed, wiping out vast microbial kingdoms that couldn't handle the change. Imagine that. The gas that gives you life was a mass killer. You hover now over one of these devastated zones, an ocean basin where once thriving anaerobes are vanishing. Their habitats shrink as oxygen zones expand. In their place, new forms begin to appear. Microbes that like oxygen, that use it to generate more energy, that move faster, build bigger molecules. It's evolution's version of a software upgrade. And over time, this oxygen doesn't just float around. It seeps into every part of the planet-altering rocks, interacting with methane in the atmosphere, changing rainfall patterns, cooling the Earth. Yes, cooling. As methane, a potent greenhouse gas, is destroyed by rising oxygen levels, the planet enters a chill. Some scientists think this triggered snowball Earth events, global freezes so extreme the oceans may have been covered in ice from pole to equator. Fringe theories suggest this might have nearly stopped evolution in its tracks. Others argue it was a necessary shakeup, forcing life to adapt, specialize, and diversify once the ice retreated. Either way, the world is never the same. You look down again at the ocean's surface. Where once there was only shadow and iron, now you see flashes of blue, true blue. The kind that comes when light scatters through oxygen-rich air. The kind that makes the planet glow from space. Earth is finding its color. In this new light, the oceans start to sparkle differently. Photosynthetic microbes grow faster, more confident. They carpet the shallows, form algal blooms, even drift into deeper waters. And with them comes the oxygen revolution, a slow, bubbling, planetary transformation that touches every molecule. It's still not a place you'd want to vacation. The air would burn your throat. The UV rays would crisp your skin. But compared to a few 100 million years ago, it's practically a spa. Your final image tonight, the rising sun over an oxygen-scented tide pool. The light is softer now. The water glimmers, not just from heat, but from clarity. And the sky, it's starting to hint at blue. A color earned, a color built, bubble by microbes with no idea what they were doing. You owe your next breath to them. Let your mind drift deeper, now away from the softening skies, away from the oxygen bubbles, and back into the ocean. This time you're diving into one of Earth's oldest secrets, the rise of structure. The seas are no longer just chemical chaos. The oxygen trickling into the atmosphere has stirred things up, not just by killing off the older anaerobic microbes, but by unlocking a new level of biological possibility, organization. Tonight, you're floating beside the planet's earliest architects. You wouldn't recognize them at first. No bones, no shells, no jaws or eyes, just soft-bodied creatures, ghostly and gentle, drifting in the shallow waters. This is the Ediacaran period Earth's awkward teenage phase. After billions of years of microbe-only drama, life starts experimenting with form. The water is clearer now, thanks to the declining iron content. More sunlight reaches deeper. More oxygen fuels bigger. More complex cells. And complexity loves to organize. You glide past a vast underwater plain where the seafloor is dusted with strange flattened life forms. They look like pancakes, or maybe ferns, or cushions. Scientists still argue what many of these ediacaran organisms actually were. There's Dickinsonia, with its ribbed oval shape somewhere between a slug and a bath mat. There's Charniodiscus, which looks like a feathery sea pen anchored in the sediment. And then there are odd tubular things, quilted things, fractal things, no mouths, no limbs, no skeletons, just a quiet forest of immobile shapes, soaking up nutrients from the water, or from sunlight, or maybe both. Honestly, we still don't know. Mainstream science considers the ediacaran biota to be some of the first multicellular organisms, a major leap from the single-celled life that had dominated for eons. For the first time, cells are cooperating at scale. They're forming bodies, dividing up jobs. Some are built to absorb, some to support, some to move, well, wiggle, slowly. Historians still argue whether these were animals, fungi, or an entirely extinct kingdom of life. Their fossils are rare and their impressions faint. But we know this: they were the first to explore size, shape, and maybe even behavior. Here's a fringe favorite, and some paleontologists suggest that Dickinsonia and its cousins may have had a primitive nervous system, a kind of decentralized response to their environment. Like jellyfish or slime molds today, they may have felt the ocean in ways we can barely understand. You pause beside one, watching it pulse ever so slightly with the tide. Not hunting, not fleeing, just existing. Patient, spongy, timeless. And here's the thing: structure changes everything. Once life gets big enough to be seen, it also becomes big enough to affect its surroundings. Ediacaran organisms help stabilize sediment. They affect currents. They even ironically make themselves vulnerable, because where there's structure, predators aren't far behind. But that's a story for a later chapter. Tonight, let's stay in this quiet world of soft bodies and soft light. Drift with the slow rise and fall of ancient waves. Watch these early creatures reach upward, maybe to catch more nutrients or light, or simply to stretch. The ocean is becoming layered with life. Shallow zones teem with microbial mats and primitive colonies. Deeper shelves are home to still strange, soft-bodied communities. And in between, life begins to occupy niches. Even the seafloor changes. Once just sediment and stone, it's now textured with living things. Slimy domes, quilted impressions, wavy trails where something may have crawled or wiggled across. This isn't a bloom, it's a creep. Life spreading outward, not upward, not yet. Now here's your quirky science note. The earliest evidence of movement, yes, purposeful locomotion, comes from this era. Fossilized trackways show something was slithering across the seafloor, disturbing microbial mats as it went. We don't know what made the tracks. We've never found the creature itself, only the trail, a whisper of intention, a suggestion of choice. And that, friend, is the first hint of behavior. Think about that. A soft-bodied, mouthless thing decided to go there instead of staying here. It left a mark, a path, a story. In that trail lies the beginning of nervous systems, sensory input, maybe even memory. And as life experiments with shape and motion, the stage grows larger. The oceans now offer microclimates, zones of temperature, light, salinity, tidal inlets with rich organics, deeper basins with cool stability. Each one offers new pressures, new chances to innovate. Some organisms get flatter to absorb more. Others rise upward to anchor in currents. A few may have even begun to bend, twist, respond. No eyes yet, no bones, but movement has arrived. And with movement comes the first suggestion of personality? Too soon to say. But you can't help feeling that some of these creatures, resting in their quilted stillness, are aware of the water brushing over them. They know the tides, and they're waiting for what comes next. You hover now dreamlike above the Ediacaran seafloor, still quiet, still soft. But something's shifting. Not the creatures themselves just yet, but the pressure of evolution. The Ediacaran period is drawing to a close, and what comes next is teeth. Welcome to the Cambrian explosion. That phrase might sound dramatic, and for once, it's earned. In just a few tens of millions of years, a blink in geological time, Earth's oceans go from tranquil quilt gardens to a crowded rave of wriggling, biting, swimming, armoring weirdos. You drift into this world slowly, your presence met not by silence, but by movement. Tiny creatures dart past. Spindly limbs churn through the water. Soft-bodied animals now come with appendages, segmented bodies, bristles, flaps. Some even have primitive eyes, spots that can sense light and dark. It's like nature stumbled upon the design folder marked Options and then hit Select All. Mainstream paleontology dates this burst of diversity to about 541 million years ago. The fossil record explodes, hence the name, with new body plans, what scientists call phyla. Most of the major animal groups we know today, arthropods, mollusks, chordates, trace their roots to this era. Historians still argue what triggered the Cambrian boom. Was it rising oxygen levels, now finally high enough to support complex tissue? A shift in ocean chemistry suddenly rich in calcium for building shells? The invention of eyes prompting an evolutionary arms race? Or maybe it was all of it, together, at once. And the result? A prehistoric underwater fashion show like no other. Look, there's Anomalocaris, the sea's first real predator. Over 3 feet long, huge for the time, it cruises through the water with undulating side flaps in a circular, tooth-lined mouth that looks like it belongs on a sci-fi movie poster. It has compound eyes. It can see you near the sea floor. Strange armored worms dig through the mud, early ancestors of today's segmented creatures. Their backs are plated, their undersides bristled. These are the first to truly burrow, transforming the seafloor into a living, breathing terrain. Life is no longer just floating or anchored. It's hunting, it's digging, it's fleeing. The rules have changed. You glance down at a creature shaped like a submarine with legs opabinia. It has 5 eyes, a long tube-like body, and a flexible trunk with a claw on the end. Evolution is clearly in a phase of try everything once, maybe twice. Nearby, Wiwaxia glides across the floor, if you can call what it's doing gliding. It looks like a slug wearing armor made of tiny scales and big upright spines. Is it a mollusk? Is it something else entirely? No one agrees, but it's fabulous. And then there's Hallucigenia. Yes, that's the real name. An upside-down mystery with legs that might be spikes and spikes that might be legs. Scientists took decades to figure out which end was the front. That's the Cambrian, a time of biological improvisation. Fringe theorists love this period. Some argue that we may be missing a whole category of now extinct organisms that don't fit into our tree of life. That maybe Earth was experimenting with multiple designs for complex life, and only a few survived. Mainstream or fringe, everyone agrees something special happened here. Let's take a moment and look around. The ocean is alive in every direction. Filter feeders flap their feeding appendages. Predators dart. Burrowers ripple beneath the seafloor. And now, at last, we see skeletons. Not bony, but hard. Shells, plates, spines, for defense. For support. With this rise of predation comes the rise of protection. This is evolution's most honest moment. Make yourself harder to eat or don't get eaten at all. Oxygen is no longer a luxury. It's the engine. It powers muscle movement, vision, rapid reactions. And with it, life reaches a new tempo. But even in this excitement, one truth remains. The ocean is still home. Life hasn't left it yet. Not even close. Everything you see is floating, swimming, or clinging. No one's walked on land, no one's taken a breath of air. But all the tools are being forged here. Nervous systems are becoming centralized. Sensory structures are evolving. Some creatures even show signs of cephalization, a fancy word for having a head. Where the senses go, brains follow. Imagine that. The first time something could see danger. Feel the current. Decide which way to swim. Not react. Decide. That's a quiet kind of miracle. And here's your quirky side note. Fossil beds like the Burgess Shale in Canada preserve Cambrian creatures so well, we can sometimes see impressions of their guts from 500 million years ago. That's how sudden and dense this explosion of life was. It left its fingerprints everywhere. So now you drift in a sea not just of creatures, but of possibilities. Every flap, spike, eye, and fin is an experiment. Some will work, some won't. But the ocean no longer feels young and empty. It feels full, like a city stirring at dawn. One last look before you drift onward. A small, worm-like creature wriggles near the bottom. It's primitive, lacking armor. But inside it, a tiny notochord, a stiffened rod that might someday become a spine. Yes, a spine. This might be your great-great-great-great-great-grandworm. Say thank you. The ocean is full now of movement, of innovation, of sudden strategies no one asked for but evolution delivered anyway. Teeth, eyes, armor. But tonight we shift our gaze again, this time to something more massive, more invisible. Earth's wandering crust. You float higher above the Cambrian waters, and below you the continents are not where they should be, because they haven't decided where they belong yet. Welcome to a world where the continents drift like lost dreams, slowly bumping into each other, forming supercontinents, breaking apart again. Land is not fixed. It wanders, dances, and reconfigures the stage on which evolution performs. This restless motion is thanks to plate tectonics, an ancient and still ongoing planetary shuffle. Deep beneath you, the Earth's mantle convects like boiling soup, slowly dragging the crust above into new positions. Oceanic crust dives under continental crust, forming trenches and volcanoes. Rifts tear open, birthing new oceans. Mainstream geology traces this dance back over 3 billion years. But during the Cambrian and the periods to follow, something big starts to happen: the assembly of supercontinents. Around this time, the land masses are collecting into a chunky puzzle called Gondwana, a vast continent that includes modern-day South America, Africa, Antarctica, Australia, and parts of Asia. It sprawls near the South Pole, covered in bare rock, primitive soils, and very little in the way of greenery. Plants haven't shown up yet. The land is still waiting for its makeover. You might think continents drifting sounds slow, and it is. Just a few centimeters a year. But over millions of years, that's enough to remake oceans, crush mountain ranges, and strangle entire currents. That's right, continental drift changes the climate. You hover now over a narrow seaway between two ancient land masses. It's shrinking. As the plates inch closer, the ocean gets pinched. Warm equatorial currents get blocked. Cold polar currents start to flow more freely. The planet cools. Again. Historians still argue whether tectonics were the main driver of these ancient climate shifts, or just one of many dominoes, but the evidence is clear. As continents move, the Earth breathes differently. Here's a delightful fringe theory. Some geologists believe that plate tectonics, this constant movement of rock and ocean, might have created the conditions for life in the first place. That without active crust, Earth would have stayed chemically stagnant, flat, uninspired, a lifeless billiard ball. Instead, the crust cracks and moves. New rock surfaces, old rock sinks. Volcanoes spew fresh minerals, and the oceans get fed, because every time a mountain erodes or a seafloor spreads, nutrients enter the water. Phosphorus, iron, calcium, the building blocks of shells, bones, and brains. Let's pause on that. Bones. Thanks to the tectonic ballet, certain areas become mineral-rich. Life takes advantage. Soft-bodied organisms start to build exoskeletons, external armor for defense. But some go inward, forming internal structures instead. Calcium carbonate becomes armor. Phosphate becomes bone. And these hard parts don't just protect, they support. They allow creatures to get bigger, stronger, more complex. You drift now beside an early vertebrate. This. It's not much to look at, about the size of a paperclip, with a fish-like shape and a stiffened rod of cartilage running down its back. But it's a game changer. Because inside that tiny body is a notochord, the forerunner of all vertebral columns. And nearby, a bundle of nerves, eye spots, gills, a hint of a brain. That, dear dreamer, is your relative. You don't descend from trilobites or anomalocaris. You descend from this little thing that learned to swim in a straight line, stiffen its back, and maybe even remember what happened yesterday. And guess what? It lived along the edge of an ocean trench, near a tectonic subduction zone, where volcanic islands dotted the sea. The crust made this possible. Let's not forget mountains either. Where plates collide, mountains rise. And when they weather, they release minerals. They feed rivers. They carve valleys. They make habitats. Earth's crust isn't just a floor, it's an engine. Fringe thinkers even suggest that the rate of tectonic movement has changed over time. Maybe Earth's crust used to churn faster, generating more heat, more volcanism, more wild chemistry. Maybe evolution sprinted because the ground itself was more restless. Now you float beside a deep trench, the ocean black below. You feel the heat rising from the boundary where plates collide. Microbes still live down there, thriving on chemical gradients. Life's oldest whispers remain, but now they're joined by echoing fish, armored swimmers, and trilobites that scurry like roaches on a wet subway floor. The world is busy, and above it all, Gondwana looms. Silent, vast, empty. For now, but not forever. Gondwana waits in silence, but not for long. Tonight you drift from the heaving trenches of the deep sea to the quiet loneliness of dry land, and it is lonely. The continents may be vast, but they are nearly lifeless. Rocky plains stretch for hundreds of kilometers, broken by the occasional volcano or shallow basin. But just beneath the surface, something stirs, something green, something small, something absolutely bold. This is the rise of land plants, the quiet conquerors of Earth's most hostile frontier. You stand now barefoot, of course, on the edge of an ancient coastal plain. The year is somewhere around 470 million BC. The air is thinner than you'd like, still low in oxygen. The sunlight hits different, too bright, harsh, unfiltered. There's no soil, no humus, no shade. But look closer. Between the cracks in the rock, where moisture gathers from mist and tidal spray, tiny green patches cling to the stone. Mosses, liverworts, possibly hornworts. No roots, no flowers, no seeds. Just stubborn mats of green. They are the first to leave the ocean behind. Mainstream science confirms these early land plants came from green algae, specifically a group called charophytes. And they brought with them the chloroplasts, pigments, and cellular machinery needed to survive sunlight and make sugar from thin air. But surviving land is no small feat. Without the buoyancy of water, gravity is relentless. The air dries you out in seconds. UV radiation stings. There are no soil nutrients, no decomposed organics, nothing to suck up or anchor to. So how do these brave little plants do it? Some develop waxy coatings to hold in moisture. Others evolve primitive, stomata tiny pores that can open and close to balance gas exchange and water loss. They begin laying down cellulose cell walls strong enough to stand at least a little. Historians still argue whether these early plants were true pioneers or just dabblers. Did they thrive inland or only hug the coast? Fossils are sparse, but spores and chemical traces tell us land was turning green, slowly, softly, unstoppably. Fringe theories even suggest that fungi arrived first, forming dark thread-like colonies across the barren surface and breaking down rock into the first primitive soil. In fact, ancient fungi and plants may have teamed up symbiotic partnerships where fungi delivered minerals and water, in exchange for sugary plant sap. The original "I'll scratch your root if you scratch mine" deal. You walk now across a patchy green plain, and beneath your feet, something shifts. Not rock, not moss, but arthropods. That's right, animals followed the plants. The first land animals were likely millipede-like creatures, feeding on decomposing algae and microbial mats. Some were detritivores, munching on decaying plant goo. Others were predators, hunting mites and early springtail-like insects. None of them were very large. Most were a few centimeters at most, but they had one thing in common: exoskeletons. These hard outer shells help them retain moisture and resist UV damage. Think of it as mobile armor in a dangerously dry world. You lean closer and watch a tiny jointed creature skitter across a rocket's legs, move in mesmerizing sync. It pauses to taste a smear of green, antennae twitching. It doesn't know it, but it's part of something huge. Because land, once cracked open, doesn't stay quiet for long. These primitive plant patches begin to expand. Spores ride the wind, mosses colonize higher ground. Over millions of years, plants grow taller, evolving vascular tissue to move water up and sugar down. Now they can stretch toward the sun, build stems, branches. Earth's skyline is beginning to rise, and with it, ecosystems form. There is your quirky fact for the night. Some of the earliest forests on Earth, like those of the Devonian period, were made of tree-like plants with no leaves. Just tall, hollow stalks and spore-spraying cones. They look like asparagus on steroids. And yet, these forests changed everything. As roots burrowed deeper, they broke down rock faster. This pulled more carbon dioxide from the air, helping cool the planet further. Oxygen levels rose. Animals on land got bigger. The Carboniferous jungles would come later, but this was the quiet beginning. Tonight you stand beneath a tree no taller than your knee. Its trunk is knobby. Its top, a starburst of green fronds. A breeze, a weak one brushes past, and a spore drifts skyward like a wish. Now look up. The sky is bluer than before. Still thin, still strange, but clearer. Plants are breathing for the planet now. Not just bubbling in the oceans, but filtering, regulating, and modifying the air above stone and moss. Earth is learning to exhale. And below you, just out of sight, seeds are stirring. Not literal seeds, those are still to come, but seeds of ideas, of forests, of bugs, of burrowing reptiles. The land is no longer waiting, it's changing. So next time you see moss clinging to a wall, or a fern uncurling in a shadowy corner of your yard, remember this: they were here long before flowers, long before dinosaurs, long before bones. They paved the way. Soft, green, patient. And now here you are. You've drifted with oxygen bubbles, hovered beside glowing vents, danced with trilobites, and strolled across mossy protocontinents. But we've arrived at the edge of one final chapter tonight, one that belongs to the first forests, the first jaws, and the first vertebrates bold enough to leave the water behind. Yes, it's time for legs. The seas are still vibrant, still loud with life. But along the muddy margins of ancient rivers and swamps, something is climbing ashore, tentatively, awkwardly, but undeniably. Welcome to the Devonian period, often called the Age of Fishes. But it's so much more than that. It's the cradle of jaws, of scales, of bones engineered not just to swim, but to step. Let's begin beneath the surface one last time. Drift through murky waters thick with placoderms armored fish, some the size of vans, with bony head shields and slicing jaw plates. These aren't your gentle goldfish. They're slow-motion tanks with teeth. The jaw is the superstar of this age. Mainstream paleontology tells us jaws likely evolved from gill arches, those skeletal supports around the throat of primitive fish. Over time, some of those arches stiffened and pivoted, forming a hinge. Suddenly, a creature could bite, not just suck or slurp. That single innovation? It changed everything. Predators got faster, prey got smarter, bodies got sleeker. It's an evolutionary arms race powered by one simple, snappy mechanism. Historians still argue whether jaws evolved once or multiple times in different lineages, but by the Devonian they are everywhere and they are busy. Here's a fringe tidbit for you. Some placoderms, like Dunkleosteus, had such powerful bite force they could shear sharks in half. That's not hyperbole. That's science with a snarl. But while these armored monsters roamed the reefs, something more fragile and extraordinary was happening in the shallows. Fins were changing. You look down at a lobe-finned fish, maybe Eusthenopteron, maybe Tiktaalik. Its fins are muscular, thick, jointed. They flex. They support weight. They're not just for steering anymore. They're for propping up. You follow it as it swims toward the shore, then pushes upward, awkward, stubby, clumsy. But it's not swimming now. It's lifting, leaning, resting on its fins like crude forearms. And then it inches forward. This is one of the first tetrapods' four-limbed vertebrates, the ancestors of every amphibian, reptile, bird, and mammal to come. You are watching the first walk. Imagine that. A fish gasping in warm, oxygen-rich air, its skin drying, its eyes scanning the surface, no longer the depths. Its bones adapting sturdier vertebrae, stronger wrists, lungs stealing oxygen directly from the sky. The first land animals aren't graceful. They're salamander-like, squishy, uncertain. But they make it. They change everything. Because once limbs arrive on land, so do ecosystems. Forests grow denser. Trees reel, towering woody trees start to appear, with roots that crack rock, leaves that filter light, bark that resists rot. Above the atmosphere thickens with oxygen. Some estimates say levels climb to over 30%, far more than today. Fires spark easily. Insects grow huge. You pass a dragonfly the size of a hawk, its wings humming like parchment drums. It skims over a marsh where amphibians lurk, blinking in the shade. The Carboniferous world is swampy, teeming, buzzing. You pause beside a club moss tree, over 30 meters tall. Its leaves are needle-thin. Its bark bears diamond-shaped scars. It's not a flower. There are no flowers yet, no fruits, just spores and cones and wind. But this world is layered. Canopy, underbrush, mud, water, leaf litter, predator, prey. And beneath it all, the rocks hum. Tectonic plates shift. Mountains rise. Volcanoes burp quietly in the distance. Here's your quirky final moment. Some early tetrapods evolved extra fingers. One fossil shows 7 digits, another 8. Evolution was playing with the blueprint, unsure how many toes a walker really needs. Eventually 4 limbs and 5 digits stuck, because it worked. And so your own hands, your fingers, knuckles, shoulder blades are the legacy of fish that crawled ashore. Not for conquest, not for glory, but because a tide pool dried out and they had to move. Simple as that. Now close your eyes and picture the landscape you've just wandered. Shimmering hydrothermal vents, rusty red seas, jelly-bodied dream creatures, glassy trilobites, moss on barren stone, forests without flowers, dragonflies bigger than cats, and somewhere under ferny shadows, a quiet breath drawn by the first amphibian. This world is gone, but not lost. It still lives inside you. Now let's let the layers settle. Imagine Earth not as it is, but as it was. Slower, heavier, wrapped in haze. The oceans warm and endless, lapping at continents still deciding where to rest. Everything moves with purpose, but without hurry. No noise, no urgency, only patience. The moss still glistens with dew. The trilobites still wander like living compass needles across the ocean floor. In the forest, nothing rushes. Even the dragonflies, giant though they are, float like feathers caught in amber wind. The air feels thick with time. And as you breathe out, you release your own little cloud of carbon, a tiny exhale added to a planet that once learned to breathe. Close your eyes if you haven't already. Let the soft light fade to dusk. Let the lapping tide slow to stillness. Let the last of the fern shadows curl back into the soil, and the glow of distant volcanoes dim like coals sinking into the Earth's memory. The rocks are still here. So is the water. So are you. Every joint, every cell, every hair and breath is built from atoms that watched those early forests grow, that swam in primordial oceans, that survived volcanic winters and oxygen booms. Sleep now, fellow fossil in progress. You've wandered far, and in the morning the ancient earth will still be beneath your feet, quiet, old, and waiting.